In this lesson, we're going to go over Gauss-Jordan elimination and reduced row echelon form. This is another matrix method for solving linear systems of equations in three variables. It is very similar to Gauss elimination and row echelon form, but there are a couple of differences that we'll talk about today. So our objectives are to understand Gauss-Jordan elimination, to understand reduced row echelon form, and then we'll be given a system of linear equations in three variables. We'll be able to put together our augmented matrix, use Gauss-Jordan elimination now, and get our matrix into reduced row echelon form to solve a system of equations. So Gauss-Jordan elimination, this method is very similar to Gauss elimination, but instead the goal is what's called reduced row echelon form. Okay, so it's a matrix method to solve systems of linear equations. We can do the same row operations where we can interchange two rows, we can multiply each entry in a row by the same non-zero number, and we're allowed to add and subtract two rows. In this case, again, our goal is reduced row echelon form. So notice, to the left of our vertical line, our coefficients, we're looking really for ones and zeros because right away, this would give us x equals a and y equals b. There's no back substitution, unless there's infinitely many solutions, with reduced row echelon form. Okay, we have x equals 1, this would be y equals 0, and z equals 2. Okay, so this form allows us to get the solution right away. Okay, reduced row echelon form, so the first non-zero entry is a 1. We form a diagonal of 1s, and all of the other entries to the left of that vertical line are zeros. So what we mean by that is 0, 0, 0, 0, 0, 0, okay? And then rows made up of all zeros are at the bottom of the matrix. Example 1. So the augmented matrix below is in reduced row echelon form and represents a system of equations. If possible, solve the system. So what we have right away is this first would be x is 6. We have y is equal to -2, and z is equal to 8. So our solution here would be 6, -2, 8. Remember, these are three planes, and this is the ordered triple as to where they intersect. Example 2, the augmented matrix below is in reduced row echelon form and represents a system of equations. If possible, solve the system. So notice here, if we were going along, we would say x is 1, y is 5, and then we get 0 equals 16. So really this means no solution. Okay, so if you get something that's not true like that in any of your steps, we can conclude the answer is no solution. Okay, so solving systems in three variables using Gauss-Jordan elimination. Just as a reminder, we could have one solution, no solution, or infinitely many solutions. We have to watch out for parallel and perpendicular and identical planes. I'm used to saying parallel and perpendicular lines. Parallel and identical planes. So again, parallel planes. These planes are parallel because the ratio of the coefficients, so to the left of the equal sign, is the same. So you multiply 2x by 3 to get to 6x, 2y by 3 to get to 6y, 2z by 3 to get to 6z, and they're equal to different constants. We can't multiply 5 by 3 to get to 16, so the planes are lying like this. Okay. Identical planes would be something like x plus y plus z equals 4, 2x plus 2y plus 2z equals 8. These are identical. You multiply everything by 8 in the first equation, or by 2, I'm sorry, in the first equation to get to the second equation. So these planes are identical. Okay, so remember that whatever solution we have has to satisfy all three of the equations in the system. Okay. All right, so solving systems using Gauss-Jordan elimination, it's very similar. We just take a few extra steps to make sure that our matrix is in reduced row echelon form. Example 1, solve the following systems of equations using Gauss-Jordan elimination. So we have our three equations. The first thing is to put them into the augmented matrix. So this is 1, 3, 2, -2, 1, 3, 4, -1, -6, and then we have 0, -10, -14. So what I do when I do this is I go column by column. So in that first column, I'm making sure the 0 or the 1 is in the correct place. Okay, so the 1 is where it's supposed to be, and now I need to get this 3 and this 2 to be a 0 using the row operations. So first I'm going to start out with taking row 2 plus negative 3 times row 1 because I want to have negative 3 and positive 3 added together. Okay, so 3, 1, negative 10, and then I'm going to multiply row 1 by negative 3. So that would give me negative 3, 6, negative 12, and 0. So I add these together and I get 0, 7, negative 13, negative 10, and this is going to become my new row 2. So on the next slide, I'm going to rewrite everything except for row 2 is going to become 0, 7, negative 13, negative 10. Negative 2, 7, 3. Okay, so I'm almost there for my first column. I need to get 2 to be a 0. So I'm going to take row 3 plus negative 2 times row 1, and that becomes my new row 3. So I have 2, 3, negative 6, negative 14. And then if I multiply row 1 by negative 2, and I add them together, 0, 7, negative 14, negative 14. Okay, so I'm going to rewrite what I have, replacing row 3. Okay, so next I need to work on column 2, and I really need to get the 1 in this position here. But looking at my rows, I think I would rather divide row 3 by 7 because those numbers divide by 7 a little bit easier than the numbers that are in row 2, and then I'm going to interchange those two rows. Okay, so what I'm going to do is I'm going to take row 3 divided by 7, and then I'm going to switch row 2 and row 3. Okay, so if I divide by 7, that gives me 1, and divide by 7, okay, and then you can interchange the two rows. So this is going to become row 2, and row 2 will become row 3. Okay, so you're allowed to interchange rows. In the steps where it said that you can multiply any row by a non-zero number, division by 7 is the same as multiplication by 1/7. Okay, so let's write what we have. We have 1, negative 2, 4, and 0. 0, 1, negative 2, negative 2, 0, 7, negative 13, negative 10, and then we keep going. So for the second column, the 1 is where it's supposed to be. I need to get this negative 2 and this 7 to be 0, so I'm going to start. I'm going to take row 1 plus 2 times row 2. So row 1 and 2 times row 2, and I add them up. So I get 1, 0, 0, negative 4, and this is going to become my new row 1. So on the next slide, I'm going to rewrite this and follow along on my paper. Okay, and next I need to get my 7 for column 2 to be all set up on the way to reduce row echelon form. So I'm going to take row 3 plus negative 7 times row 2, and that's going to give me my new row 3. So row 3 is 0, 7, negative 13, negative 10, and if I take negative 7 times row 2, this is negative 7 times row 2, negative 7, 14, and 14. Add them up, 0, 0, 1, and this is 4. Okay, this becomes my new row 3. Next slide again. 1, 0, 0, negative 4, 0, 1, negative 2, negative 2, 0, 0, 1, 4. So notice this matrix is actually what's called row echelon form. It's not yet in reduced row echelon form. To get it to be this negative 2 would need to be a 0, and then we'll have it in reduced row echelon form. So let's practice that. We are going to take row 2 plus 2 times row 3, and that's going to give me my new row 2. Okay, so row 2 is 0, 1, -2, -2, and 2 times row 3 is 0, 0, 2, and 8. I add this together. Okay, and that becomes my new row 2. So I'm going to write it on the next slide. I have 1, 0, 0, -4, 0, 1, 0, 6, 0, 0, 1, 4. Okay, and then right away, this is x is -4, y is 6, z is 4. So my solution here is -4, 6, 4. So that is my ordered triple. Okay. Let's do one more example. Solve the following system of equations using Gauss-Jordan elimination. Okay, so step 1 is to put this into an augmented matrix. So I have 3, -5, 6, 14, -9, 15, -18, -39, 9, -15, 18, and 39. Okay, so remember what I said about parallel and identical planes, that you can take the coefficients of one, multiply them by something to get to the other, or maybe they look exactly the same. So when I see things like that that are multiples of each other, I start there rather than starting with getting the one in the correct column, just to see what's going to happen, because it could lead me to infinitely many solutions or no solution. So row 2 and row 3 have the same numbers but with opposite signs. So if I add those together, I'm going to get all zeros right away. So row 2 plus row 3, new row 3. And if I add these together, I get all zeros. So let me go to the next slide. Okay, so the temptation is to conclude that there are infinitely many solutions, but we have to be very careful. The first line could still be, or the first equation, I'm sorry, the first plane could still be parallel to the other two. Okay, so now we need to check for that. So notice here we have row 1 and row 2. If I multiply row 1 by -3, I can get to row 2 except for the constants 14 and -39. So I'm still going to work with that to see what happens. So I'm going to take row 2 plus 3 times row 1, and let's see what happens. So row 2 is -9, 15, -18, -39, and 3 times row 1 is 9, -15, 18, and this would be 42. If I add them together, 0, 0, 0, 3. So now let me write what we have in our matrix. So looking at row 2 and row 3, it can't be no solution and infinitely many solutions at the same time. So what's happening here? If we look back at our equations, we can take a look and see. Okay, but the answer is going to be no solution. Because there's not going to be an ordered triple that will satisfy all 3 equations. So let me rewrite our equations and show you what's happening here. And then we have 9x minus 15y plus 18x equals 39. Okay, so notice this is equation 1, equation 2, equation 3. Equation 2 times -1 everything, so -9x, 15y, -18x, 39, times -1 gives us equation 3. So this means that these two planes are the same. Okay, so that's why we got all zeros on that bottom row. Okay, so equation 2, equation 3 is an equation of the same plane. So they would just look like one sheet of paper. Okay, now looking at equation 1 for the coefficients, I could multiply these by 3, and I will get equation 3. But what won't give me exactly equation 3 is if I multiply 14 by 3, I get 42. Remember what we talked about. If the ratio of the coefficients is the same, these lines are parallel. Okay, so what's happening here is 2 and 3 are identical. 1 is parallel to 2 and 3. So that's why it's no solution, because even though 2 and 3 are overlapping, all of their ordered triples are the same. Equation 1 is parallel to those, so there's no ordered triple that's going to satisfy all 3 of our equations here. Okay, so that's why this is no solution. I will make a note here that when we got to zeros, when we got to all zeros here, we have to be careful and check for something like this. However, if in the first step we would have gotten this 0, 0, 0, 3, it would have been no solution. We would not have had to go any farther in investigating this. Okay, so if you have any questions, please feel free to reach out to me.